So before we do that, let us understand or let us recall what did we do. So do you guys already know that or prerequisites. So you guys already know that what is the variation of pressure with depth. This you guys already right. So if let's say if we have this beaker and if we are calculating the pressure at this depth, right? Then what would be the pressure at this point? So let's say this is PA. So what would be the pressure? Pressure would be at this point, let's say this is B. So that would be the atmospheric pressure at the top plus rho GH. Right, guys?
Yes,
Yes,
sir.
sir.
That is how the pressure varies, right? So this is so P2 is P1 plus rho GH. That would be. Now we have also understood that, okay, let's say you have this circle, right? So this circle is a part of some, so this arc is part of some circle, right? So then it will have some radius. So this would be the radius of this circle. Clear?
Yes,
Sir.
sir. Yes, sir.
So if I draw this arc, so it will have a radius at, okay, this is another thing. The third thing that we have to remember that if we have one membrane which is, so let's say if we have a two-layer system. So let's say we have air, right, and then water droplet. So this is a two-layer system, right? One layer is inside, the other layer is outside. So this is a water drop. Let me make a. This is water drop, right? And this is the wow, this one is very big one. The inside is water, outside is air, right? This is the water drop. And we talked about that it will have pressure. One would be the pressure inside, the pressure outside. Right, guys? Right.
Yes, sir.
And this is the curved part. So inside is the concave region. So which pressure would be greater? Pi or Po? Which would be greater? Yes. Which would be greater? Okay, so this we did in the previous class that this part is called the concave part, right? And I showed you guys an example that if you press notebook, right? So if you press your notebook from here, then make this, it will make this kind of a shape. So this shape is concave one. This one is the convex one. So then we saw that always the concave one has the greater pressure, right? So this pressure is always greater than the convex one. This thing we learned in the previous class, right? Oh, so
Yes, sir.
P P inside would be greater than P outside, because this is the concave part, right? This is the concave part and this is the convex part. And we see in the example of water drop that this difference was, this excess pressure was how much? This excess pressure was 2s by the radius of this water droplet, right? And this thing we calculated from two things by calculating the work done. So these things we calculated from work done and from surface energy. All these things we calculated, right? Okay, so you guys please go back to the derivation that how to do the result. And this was for the case of drop. But for the bubble case, right, for the bubbles, we had three layers, right? We had three layers. So this was air, right? And then we had this bubble layer, which was liquid, right? So air and liquid, and this is liquid again, and then air. So we had three layers. So this was P inside, this was P outside. And when we calculated the excess pressure of bubble, we got 4s by R. Do you guys remember these things? Yes.
Yes, sir.
So whenever we have three layers, this would be 4s by R. Whenever we have two layers, this would be 2s by R. So let's say that this is one case, this is second case, and the third case is that I have put the bubble in the water, right? So you guys have seen those Pepsi and carbon diffused drink that you have those bubbles popping out of inside the Coca-Cola or whatever food drinks you have, right? So we have the bubbles in the water. So how many layers are there? We have this layer, right? This is liquid, and this is air, and outside is also liquid again. So how many layers are there? Bubbles in the water. How many layers? This is liquid. Whole thing is liquid, and then this air. So we only have two layers, right? So again, this P inside and P outside would be how much? That would be 2s by R. So keeping these things in our mind, let us uh, let us understand about the capillary ducts. These we call these. Okay. So now let us understand capillary ducts. So in the capillary ducts, what happens is that if you place a very thin cylindrical tube, right? If you place a very thin cylindrical tube in the water, right? So this is the water layer, and due to surface tension, right? Due to surface tension, what will happen is that in this surface, it will create this kind of surface, right? So if I zoom this thing, right? If I zoom this thing, so this surface would be like this, Okay. So this is let's say this shape is what part is concave, what part is convex? Can you guys tell me what part is convex, what part is concave? Oh my. So down part is convex. Yes, absolutely right. So this is a convex one. This part is a concave. Yes, absolutely right. So this is a concave one. Good. Yeah, upper part is concave. So in let's say that this is in the air, right? So let's say that this is Pi, this is Pi, and this is Pi, and this is Po, right? So we know that this is concave part. So in here the pressure is more, and in here the pressure is less, right? So in here and all these points have same pressure, right? So what this pressure will do is that it will apply some pressure from this side because this has a lower pressure. So it will increase the height of this because this has a lower pressure. So this pressure will put some pressure in this region and it will be increased. So the height, so the actual diagram would be this, right? The height will increase. So now the water will rise to this height. So water will rise to this height. Okay. And now let's say this is PO. Right. I'm writing this point PO. So this is PO. Right. And the water has risen up to this height. So is this thing clear that why this has risen, guys? Is this thing clear? Yes, guys, is this clear? Because these all these points are at the same height, so all these have same pressure, right? But you see that this pressure is in here. This pressure is concave part. This is convex part. So inside this point, this pressure is less. So to increase this pressure, right? To balance this pressure, the water will put some pressure from inside, right? And then it will rise. So it will rise up to some height, right? So this is a
Yes, sir.
P, yeah, this is a PO, and let's say this is, so let me write it, right? So this is PI, this point is PO, and this is again PI, because all these are atmospheric pressure, right? So this is in the contact of air, so all these are atmospheric pressure. So this point is also Pi. And what do we know? Right. What do we know that this is a part of a circle, right? This concave part is a part of circle. So its radius would be what? Its radius would be this R, right? So it will have some radius. And the surface tension is acting tangentially to this region, right? So the surface tension is acting in this way. So this is the surface tension. This is angle theta, right? And we know that these are perpendicular, right? So these are perpendicular. So, and if I draw a distance A from here, right? So this is the radius of, so you have a cylinder, right? You have this cylinder, so cylinder has this radius, right? This part is circular, so it has some radius A. So similarly, this radius is A, right? You don't know that what is this radius of the concave part. Only the given thing that you know is that the radius of this cylinder, right? So we'll come to this cylinder part later. But we know that what would be the excess pressure. Can you guys tell me what would be the excess pressure? What would be the excess pressure, guys? Yes, guys, what would be the excess pressure? Yes.
Sir, can you repeat what you just said?
Yes, I'm asking that we already know that what is the excess pressure, right? So
Yes, sir.
what would be the excess pressure, guys? That we already know.
4S by R?
We have only two layers, right? One and two, only two layers. So that would be 2s by r.
2S by R.
Yeah, so this is absolutely correct. Good. And we know this thing. And we also know that, let's say if this is Pi, right? This is Pi, this is Po, and this is H. So from variation of depth, right? So from variation of depth, what do we know? We know that these points are at same distance, right? So Pi would be this point and this point. So Pi would be how much? That would be Po plus rho gh. Here, guys, from Pascal's law, right? This point, this point, this point. These are all same point, right? These are all same point,
Yes.
Yes, sir.
and this is at certain height, right? So from here, this is Po, right? So we have this thing. This point is Po, this is Pi, and this height is H. So we know that at depth, Pi would be this thing. So if I calculate Pi minus Po, so that would be rho gh, right? So rho gh is this thing, rho gh is this thing. So then I can calculate this height. So let's say this is first equation, this is second equation. So rho gh would be how much? That would be 2s by r, right? So I want to calculate the capillary rise, right? That is what my goal is, that how much this water will rise, right? So this is what I want to calculate, capillary rise. So let us calculate this thing. So H would be 2s by rho gr. But I don't know the radius of this concave part, right? I don't know the radius of this concave part. I know this angle, I know this angle and the radius of the cylinder. So I have to relate this theta and A with this radius, right? So how can I relate that? So this is theta, this is 90, so this would be 90 minus theta. So this would be how much? This would be how much, guys? Okay, let me draw this thing in here. So this is theta, right? These two are perpendicular, so this is 90 minus theta. and these two are perpendicular, right? So if 90 minus theta is this, so what would be this angle? What would be this angle, guys? Yes, did you guys understand?
Sorry, sir.
Okay, let me draw this again. So what do we have? We have this part, and this is the concave part. So what did I tell you guys? That the radius of this part, right, which is making the drop or whatever, the bubble. So we know that this thing is equal to this radius part, right? So this would be the radius of that concave part. And we don't know this radius. We only know this radius of this cylinder that we have, right? Whatever the capillary that we have put, so we know the radius of that capillary. We don't know the radius of this concave part. We know this angle, whatever this contact angle is, right? We know this angle, we know this A radius. So the idea is that we have to relate this radius with this cylinder radius. Is this thing clear, guys?
Yes, sir.
Okay, so we have this theta. This is perpendicular, so this would be 90 minus theta. Clear?
Yes, sir.
And again, these ones are perpendicular. So this is 90 minus theta, so this would be how much? That is what I'm asking. Yes, everyone, Rishita, Ilham, Amna, Akim, you guys, tell me what would be that angle. Let me draw this thing in here. So you guys, please think about that. We have this theta, this one perpendicular. So this plus this would be 90. So if this is theta, so this would be 90 minus theta. Now this one and this one, they are perpendicular. So if this is 90 minus theta, this would be how much? That is my question.
90 minus 2 theta.
90 minus 2 theta. Okay, so let's say this is x, this is y. X plus y is how much?
90.
90. Because these are 90, right? And x we need to find out. We know that this is y is 90 minus theta. So if I take this in the other side, 90 minus 90 plus theta, so this would be theta. Clear?
Yes, sir.
Yes, sir.
Okay, so now let us get back to this part. This is theta, right? This is A. I will erase the part which is confusing. So this is A, right? Now can we relate this A, R and theta? Can we relate that? So this is base, this is hypotenuse. So what relates base and hypotenuse? What relates base and hypotenuse?
Sine.
B by H is sine theta. Cos theta relates base and hypotenuse, right?
Yes, sir.
So cos theta would be base is how much? A, hypotenuse is R. So I want to calculate this R, which would be A by cos theta, which is A sec theta. Right, so I will put this value in here. So this would be how much? So this would be 2s by rho g, and let me write it as A by cos theta. This cos theta will go here. So this is 2s cos theta by rho g. So this would be the capillary rise. So this capillary rise is dependent upon what? This is dependent upon surface tension. This is dependent upon rho. This is dependent upon this the radius of the capillary that we are putting, right? So you guys can tell me that surface tension should be larger and this theta also. So this is also depending upon this theta, right? So we can clearly see that if theta is small, then this would be larger. If A is small, then rise would be larger. If density is small, then again this H would be larger. If surface tension is higher, then it would be larger. So this capillary rise is dependent upon these parameters, right? So this is the capillary rise. So what is capillary rise? So the rise in level of the liquid in the capillary to surface tension is called capillary rise. And we have seen that what is the value of this capillary rise? So this is 2s cos theta divided by root g. And what are the things that we used? So first we used that for a concave part, the pressure in the concave region would be larger, the pressure in the convex region would be smaller. So if this is the scenario, then the pressure will create, so this pressure is low. So outside pressure will apply and it will try to balance the pressure, so it will increase this level. And then we applied this second part, right? So the second part we use is the variation of pressure at depth, right? So we saw that this is the concave region, and we know that for the concave region, the excess pressure is this much, right? So in this part, we were getting a structure like this. So we assume that this is a part of the sphere, and then we made a radius, and then we wrote this excess pressure. Then we use the idea of excess pressure. So this was 2s by r. And then we use the idea of trigonometry to relate this radius with the radius of the cylinder. So that is all that we did in this capillary line. So is this clear, guys?
Yes, sir.
Okay, then please note it down. So please note it down. And if you guys have any question, please let me know if you guys have any question. Yeah, whenever you guys want me to scroll down, please tell me.
Done, sir.
Yeah. Yeah, whenever you guys want me to.
Done, sir.
Yeah. Okay, please. Yeah, whenever you guys have noted it down, please tell me.
Done, sir.
Done. Okay, so everyone noted? Yes, guys, noted everyone.
Yes, sir.
Okay, so now let us do one question. So this chapter is complete. Right, this chapter is complete. This was the last topic. So yeah, so now we'll start the new chapter. But before we do that, let us do one question, right? So let me start this chapter. And this question is from yeah, this question is from A. We will question from yeah, yeah. Okay, so what is the question? Yeah, so this is the question. Right. The lower end of a capillary tube of diameter 2 millimeter is dipped 8 centimeter below the surface of water in a beaker, right? So what is the pressure required in the tube in order to blow a hemispherical bubble at its end in water, right? So we have a bubble, right? Remember we have a bubble. So this bubble, what is the excess pressure of the bubble? How much is that?
Yes.
Yeah, so this is
Atmospheric pressure?
no, I'm asking that what is the excess pressure of the bubble? This has two layers, right? This has two layers, so excess pressure of bubble is 4s by r, right? Right, guys.
Yes, sir.
But this bubble is what we are doing. So we have this beaker, and the water is inside this beaker, and we are putting a tube, right? We are putting a tube. So let's say the bubble is here. So we are pushing this bubble in here, right? So now the bubble is where? Bubble is inside the liquid, right? Bubble is inside the liquid, so we have to find the excess pressure inside the liquid. So that would be how much? That would be 2s by r, right? Right,
Yes,
guys?
sir.
Yeah, so first we have to find out what is the pressure at this height, right? And then we can calculate this excess pressure. So this first we have to find out what is the pressure of this bubble at this point, right? So that would be, this is in contact with air, right? So this will have atmospheric pressure and the height of this tube, right? So that would be how much? So PO total, that would be how much? That would be PA plus rho GH, height of this whatever this capillary tube, right, guys?
Yes, sir.
And then what would be, so we know that how much is the atmospheric pressure. So how much is the atmospheric pressure? PA is 1.01 into 10 to the power 5 Pascal, right? And rho is how much? So rho is 1000 kg per MQ. And yeah, G is how much? G is 9.8 we have to take. Okay. And the height of this thing, right? The height of this capillary tube. So that is 8 centimeter. So H is 8 centimeter, which is 8 by 100 meters. So these are the things. And then we can calculate the pressure of this bubble at this height. That we can calculate, right? So this would be how much? This would be, we are not calculating the pressure inside, right? This we have to find out. Pressure inside we have to find out. So PO would be how much? So this is the PO that we are calculating. PO would be this PA, right? And then this height. So this is 1.01 into 10 to the power 5 plus rho is how much? So rho is 1000 kg, right? Rho is 1000 kg per meter cube, and then G is 9.8. Height is 8 by. This is how much? Zeros are cancelled, and then this is how much? 1.01 and 10 to the power 5, and this is 8. So this is 98 into 8. So 1.01 into 10 to the power 5 plus 8 is 64 and 8 nines are 72 plus 6 78. So you guys tell, can we add this thing together? Can we add this thing together, guys? Yes, this is a general question.
Sir, can it be? I don't think we can.
Yeah, we cannot, because what is the order of this thing? This is 10 to the power 5, right? These are not like
Yes.
terms. These are not like terms. Either I make this like this term, or I do something about this that I can make a power of 10 to the power of 5. So let us write this thing in this way. So this is how much? This is 101 and 3 zeros, right? Plus 784. Is this correct, guys? This is clear.
Yes, sir.
So then this would be how much? This is 101784. So then this is 1.01784 into 10 to the power 5. So let me write this in here. 1.01784 into 10 to the power 5 Pascal. So, this notation, let me write it as atmosphere notation. Because both these notation are similar, right? So what we have done in the first part, we had this bubble, right, which is here, right? We want to push this bubble from here to here. So the outside pressure of this bubble is PO, right? And we calculated this PO. Now remove everything. We calculated this PO with some height, and this was the atmospheric pressure. So we use the idea of variation of pressure at certain depth. right? Is this part clear, guys?
Yes, sir.
Okay, now I want to calculate the pressure inside this bubble. I want to calculate, right? So we know that what would be the excess pressure? We already know that excess pressure would be how much? Excess pressure that would be Pi minus Pu. That is 2S by R as Rishida has. Right. So 2S is how much? Surface tension is how much? Surface tension is 7.30 into 10 to the power minus 2, right? This is 7.30 into 10 to the power minus 2. Divided by R was how much? R was 2 millimeter. Oh, so this is the diameter, right? The low end of a capillary tube of diameter. Okay, so this diameter is given, so we can calculate the radius, right? The radius of the bubble. So the bubble is this whole, right? This is the size of the bubble. So it is matching with the size of the tube. So it will have the same radius, right? So what would be the radius? Diameter is 2 millimeter. So radius would be diameter by 2, which is 1 millimeter, which is 1 into 10 to the power minus 3 meters. So this is 1 into 10 to the power minus 3 meters, right? So it will go upstairs, right? So this is 2 into 7.32 into 10 to the power minus 2 into 10 to the power 3. So this is how much? 2 to the 4, 2, 3 the 6, 7 to the 40, and 10 to the power 1. Right, so this is how much? This is 14640. So if I write it in order of 10 to the power 5, so 1, 2, 3, 4, 5. This is 0.146 uh, into 10 to the power 5 Pascal. So this would be the excess pressure, right? So this is the excess pressure, and then I can also calculate the pressure inside of the bubble, right? So pressure inside of the bubble is PO plus this excess pressure, right? Because I know that this is 10 to the power 5 Pascal. Right, so PO I have already calculated, that is 1.0178 into 10 to the power 5 plus 0.146. So these are on the same order, right? So then this would be how much? 4 and 8 and 7, 6, 13, 1, 1, 2 and 4, 6 and 1.1 into 10 to the power 5 Pascal, which is 1.164 into 10 to the power 5 Pascal. So did you guys understand this question? We had this bubble, right? We had this bubble which we wanted to push inside this deep water, right? So we had this bubble, and this had only two layers. One was inside, the other part was outside. So we calculated this outside pressure due to this variation of depth. And then from this PO, we calculated this excess pressure. And then from excess pressure, we calculated this pressure inside of the bubble. So you guys can see that this is there is some difference in pressures. Is this question clear, guys?
Yes, sir.
Okay, then you guys please note down this part and yeah, note down the question as well. And then we will start the chapter. So please note down the oh, please note it down. And then we'll start the chapter. Whenever you guys want to scroll down, just
So can you scroll down?
Yes, I got disconnected, guys. Where is it? Why? The problem. Yes, did you guys note it down?
No, sir. Last word remaining.
Yeah.
Okay, yeah, yeah. And if you guys have any doubt in this part, please tell.
Done, sir.
Done. Good. So now, hey, yes.
Sir, your voice is breaking.
Yeah, the now need is okay. So in this chapter, we will talk about the thermal properties. Right? So why my internet is not stable? Yeah, my voice is breaking too much. Yeah, I can understand. Because is this clear now? How is it now, Rishita? The internet is yeah, working very bad.
It's fine,
How is it
Sana.
now? Oh, it's fine. So in the previous two chapters, what did we understood? We understood about the mechanical properties of the solids. We understood about the mechanical properties of the fluids. Right. In this chapter, we will talk about the thermal properties of the metals. Right. So we know that the therm word is related with temperature, right? So thermal pro- properties of metal. So this of the word therm, which means temperature, right? Temperature of the matter, right? So what are the properties associated with the temperature? So we'll talk about the ideal gas equation. We'll talk about the thermal expansion and all these property, right? Charles law, Boyle's law, all these properties. We will right. So let us first understand about this temperature. Already know that some object. So it has so there would be hot water and there would be cold water. So this is the relative thing, right? It tells about the coldness or hotness of the object, right? So it's a relative thing, object or right, and it is a relative, and this temperature is a very important one, right? So it is a relative thing, and how do we measure the temperature, right? So the measurement, there are two units of temperature. One is the Fahrenheit and the other one is the Celsius, but the SI unit of temperature is Kelvin. So SI unit of temperature is Kelvin, right? And this is denoted by K, and it is a scalar quantity, right? It's a scalar quantity. And we also represent the temperature by Fahrenheit. So generally it is denoted or it is represented in degree Celsius. Right. These are the peculiar properties of temperature. And from this temperature, we define the idea of heat, right? So we define the idea of heat by this temperature. So what is heat? So let's say if you are if you have some water in the beaker and then you are boiling this water, right? So you are boiling this water, and what you are doing is that you are increasing the temperature of this water, right? So this heat is the change in energy due to, or it is also called the transfer of energy, right? So it is the transfer of energy energy due to the difference in temperature. This is what we call heat energy, right? So this is a and heat we define again very important parameter. So we define. Again, my voice is breaking, right, guys? Is my voice it's getting stuck. What is happening? What is happening today? Yeah, so okay.
So it's fine now, but sometimes like your sentences get cut off and then you come
Yeah,
back
sometimes
online.
my sentence break, right? So, yeah, maybe the internet is fluctuating a lot. Okay, so internal energy of the matter, right? So total internal energy. So total internal energy of matter is one is the kinetic energy, right? And the second one is the potential energy, right? So where this kinetic energy comes from, so this kinetic energy comes from the motion of the particle inside the matter, right? So this comes, what happened? Yeah. So this comes from the translation, rotation, or vibration of the molecule, right? So this comes from the motion of the molecules of the matter. And this potential energy, this comes from the interaction between the molecules. So, right, and this comes due to the temperature difference. So that is, this one is dependent upon the temperature. So there is another use of this temperature, that this kinetic energy of the internal energy due to the kinetic energy of these molecules, that is dependent upon this temperature, right? And the interaction between the molecules, that gives the potential energy, right? So total energy, U total, this is U kinetic energy plus U potential energy. Okay, so this is the total energy of the matter, internal energy. And then we have this thing which is called the thermal expansion. So mainly we have three kind of expansion. One is the linear expansion, and then we have this superficial and the third one is the cubic expansion. But first, what is thermal expansion, right? So if we heat some matter, right? If we heat some matter, then the internal energy changes. So we are providing some kinetic energy to those matter. So then it is elongated. So the size changes. So the size of those matter changes. And if those are happening linearly, right? Then that would be called linear expansion. So thermal expansion is what? thermal expansion is the change in size of the matter due to temperature is different or due to the provided heat is called thermal expansion, right? And if this thermal expansion
Yes.
is being done in linearly, right? So let's say what is this thermal expansion? So linear expansion is what? We have this rod, right? And we are hitting this rod, right? So we are hitting this rod. So let's say this actual length of this rod is L, right? Let me write it in capital. So the actual rod is L, but due to this provided heat, the molecule of this rod will gain some kinetic energy, and then they will move around, and then they will elongate. So then this size of this rod will change, right? But this is happening linear, right? So this is called the linear expansion. So these two distance, these two elongation. So the total elongation is delta, right? Now the length has become L prime. So the elongation would be how much? Elongation is delta L, which is L prime minus L, right? And this is happening due to change in temperature. So this elongation is directly proportional to the length of the rod and the temperature change, right? And if we remove this proportionality constant, so we will get a constant, and that is called alpha. This is L delta T. Alpha here is called the coefficient of linear expansion. Right, so this is called the coefficient of linear expansion. We'll do one question about this linear expansion. What you guys please note down these points. Right. So please note down these points. And this chapter is pretty small, so it will not down. Yeah, whenever you guys want me to slow down, please.
So can you scroll down? No, sir.
A bit up.
No, I thought you were going all the way down from total internal energy.
Yeah, I scroll down.
Yes, sir.
This is the thermal inspection. Yeah, whenever you guys have noted it down. Yes, guys are noted.
That's all.
Guys, done. Done, everyone.
Yes, sir.
Okay, so yeah, and we can figure out what would be the SI unit of this coefficient, right? So SI unit of this coefficient should be what? L by L delta T, right? Where delta T is change in temperature. So SI unit of or dimension of L is meter. This is meter, right? So this will cancel. So the SI unit of this alpha, that would be, this is Kelvin. So Kelvin inverse, right? Or we can write this as degrees Celsius inverse. So this would be the units of its coefficient, right? Similarly, we have this superficial expansion. So in superficial expansion, what happens? So in superficial, okay, yeah, okay. In superficial expansion, the change in area, the thermal expansion, right? So if there is the change in area, then that is called the superficial expansion. So what do we have? We have this rectangle, and we increase the temperature of this sheet, and the area is increased, right? So then this new area becomes Okay, so initially the area was A. Now the area is A prime. So change in area is how much? That is delta A, which is A prime minus, right? So, and this delta A is equal to, I will write directly, beta area and delta T. So that is the, and where this P is temperature coefficients of superficial expansion, right? So coefficient of superficial expansion. Okay, the time is over. So I will stop in here and I will continue from here. So in the next class, I will give you guys some time to note it down. But yeah, I will continue from there. And we will understand that this beta is related with this alpha, right? So from
Yes, sir.
dimension analysis, we can direct, yeah, from area is related by length square, right?
Yes, sir.
So if I calculate the relative error, so that would be how much? Delta A by A, this would be 2 delta L by L, right?
Yes, sir.
Right, guys? So I already know
Yes,
that
sir.
this delta L by L is how much? So this delta L by L, if I calculate from here, so this delta L by L is alpha delta T, right? So this is 2 alpha delta T, right? Because delta L is how much? Alpha L delta T. So if I calculate delta L by L from here, so alpha delta T. So this is this, and I know that